Hi, welcome. My name is Aamir Shafi and I will be presenting our paper titled Efficient MPI-Based Communication for GPU Accelerated Dask Applications. This paper is about developing a new MPI-based communication device or backend for Dask, which is a big data computation framework like Apache Spark. The outline of the talk is as follows. I will first present an introduction of the talk. This will be followed by the design and implementation of MPI for Dask, which is the name of our MPI-based communication backend. Next, I will present performance results for basic communication and application benchmarks. I will conclude this talk with a summary. Dask is a big data computing framework like the Apache Spark, and this allows scaling Python applications from laptops to HPC systems. Dask has been adopted by the NVIDIA Rapids project. The goal of this project is to support end-to-end data science pipelines on GPUs. Under the hoods, Dask converts user applications into a task graph that is later executed lazily on the parallel hardware. A key component of the Dask ecosystem is the Dask distributed library. This library forms the foundation of supporting Dask on parallel and distributed hardware. Being an asynchronous framework, this library supports execution of coroutines using the async await syntax. The async keyword is used to define coroutines, while the await keyword is used to invoke the coroutine. And coroutines are essentially basic building blocks for Python-based asynchronous applications. These can be thought of as routines or functions that can execute asynchronously. Also, they have the ability to pause during execution in order to complete any pending blocking I/O event while allowing other coroutines to execute on the CPU. Coroutines typically allow asynchronous applications to increase CPU utilization. Currently, Dask provides two communication backends. The first one uses Tornado package and makes use of TCP. The second is based on the UCX library. Since UCX is a C-based library, Dask makes use of UCXPy to interact with UCX from the Python codebase. So UCXPy is essentially a Python wrapper that provides interface between Python and C applications. This paper introduces MPI for Dask, which is an MPI-2 GDR-based communication device for Dask. This device optimizes GPU to GPU communication on cluster of GPUs. MPI-2 is central to that, and it's essentially a state-of-the-art GPU-aware MPI library that has support for NVIDIA and AMD GPUs. For the NVIDIA GPUs, it has support for advanced GPU communication features like GPU Direct RDMA, CUDA IPC, and GDR copy. In the context of this talk, we will only be using MPI-2 GDR over NVIDIA GPUs. MPI-2 is a high-performance MPI library that supports multiple interconnects, including InfiniBand. The project started in 2001 and has been empowering many top 500 systems. The software has been used in more than 3,000 organizations in 89 countries and has been downloaded roughly 1.3 million times from the OSU website alone. There are several variants of the MPI-2 library. In this paper, we use the MPI-2 GDR library that supports efficient communication between GPUs on HPC systems. The main contributions of the paper are as follows. Number 1, design and implementation of MPI for Dask. Second, integration of MPI for Dask in the Dask distributed library. To the best of our knowledge, this is the first MPI-based communication backend for Dask. We present performance evaluation of MPI for Dask against other communication devices using basic communication and application benchmarks. And number 4, and the last one, we also evaluate scalability of MPI for Dask by evaluating performance of application benchmarks on the TAG Frontera GPU system. This section presents the design and implementation of the MPI for Dask communication backend. The Dask distributed library provides several components that enable the execution of Dask program on parallel and distributed hardware. As can be seen in the figure on the right hand side, these components include scheduler, multiple workers, and a client. The scheduler is the central component and is typically the first one to start. Later, one or more workers can be started and these connect with the scheduler. Finally, the client process is started that is responsible for submitting user application to the scheduler. The connection between client and scheduler show that these two components communicate. Also, workers talk to the scheduler. The dotted edges between workers depict that workers can communicate with one another on demand. This leads us to communication requirements of Dask. Scalability. So end users would like to utilize as many compute resources as possible. Elasticity. Workers can come and go during execution. Support for coroutines. Since Dask is an asynchronous application, all communication functions need to be implemented as coroutines. And lastly, communication to from the GPU memory must be supported. This slide presents the architecture of the Dask framework starting from the top to the bottom. The top layer represents the basic Dask library that has support for data structures like Dask arrays and data frames and abstractions like delayed and future. The basic Dask package is supported by additional packages like Dask MPI, Dask CUDA, and Dask Job Queue. Dask Job Queue, for example, provide utilities for running Dask programs on HPC systems where job submission software gets involved. The next layer is the Dask distributed package. This contains components like scheduler, worker, and client. Most importantly, in the context of this paper, it provides the communication layer. As mentioned earlier, TCP and UCX devices already exist. UCX device makes use of the UCX by a Python wrapper to make use of the UCX library. The highlighted yellow boxes represent the implementation of the MPI for Dask communication device. It makes use of MPI for Pi to make use of the communication functionality provided by MPI-Based GDR. Next, we discuss the bootstrapping and dynamic connectivity support provided by MPI for Dask. There are several ways to start a Dask programs. The manual way is to run a scheduler followed by one or more workers and a client. There are some utility classes that allow facilitating the bootstrapping process using different job submission systems. We use Dask MPI to bootstrap execution of Dask programs that use MPI for Dask for communication. As the top figure shows, Dask MPI assigns rank 0 and 1 to scheduler and client respectively. All workers are assigned other ranks in a consecutive fashion. The communication API provided by Dask distributed requires different components like scheduler, workers, and client connect to one another dynamically. MPI for Dask fulfills this requirement using the async IO package. Using this package, scheduler and workers listen for incoming connections by starting a server. They call the async io.start server function. Any process wanting to connect with the server can do so using the async io.open connection function. This slide discusses the implementation of point-to-point communication coroutines for MPI for Dask. As mentioned earlier, MPI for Dask uses MPI for Pi to make use of non-blocking point-to-point functionality provided by MPI-Based GDR. MPI for Pi provides two flavors of point-to-point functions. The first set of functions start with capital letters like the highlighted send and receive and communicate serialized data stored as raw bytes. The second option is to use functions starting with small letters, and these are used to communicate Python objects. This incurs pickling, unpickling overhead. MPI for Dask uses the first set of methods that exchange data stored in buffers like CuPy and NumPy. Dask distributed can communicate very large messages. For this reason, we have implemented a chunking mechanism in MPI for Dask for large messages. The send and receive coroutines are implemented using MPI's non-blocking send and receive method. After initiating the data exchange Each coroutine checks for completion using the request.test method, as shown on line 2 and 6. Since this code is running as part of a coroutine, it is required to yield the CPU to other coroutines to avoid deadlock. We achieve this by calling async io.sleep coroutine. This section will present basic communication and application benchmark results and evaluate performance of MPI for Dask against other communication devices. The following is the experimental setup used for evaluation in this paper. We use two HPC systems that include an in-house RI2 system and the TAG Frontera GPU system. On RI2, we have used two types of GPUs including Tesla V100s and K80s. On the TAG Frontera system, we used NVIDIA Quadro RTX 5000 GPUs. 100 gigabits per second InfiniBand EDR network connects the RI2 system, while the TAG Frontera system is connected using 56 gigabits per second InfiniBand FDR network. In this slide, we present the latency and bandwidth comparison between the communication coroutines provided by MPI for Dask and UCXPy. This comparison is done using ping pong benchmark. The performance trends that we will observe will form the basis of application level performance comparison. We will also add MPI-Based GDR and UCX in this comparison, since these will provide the baseline performance for MPI for Dask and UCXPy respectively. In these graphs, we have message size in bytes as the x-axis. The left-hand graph is presenting performance of small and medium messages from 1 byte to 256 kilobytes. The y-axis here is latency in microseconds. Lower is better for this latency plot. As we can see, MPI for Dask, this maroon curve is achieving lower latency than UCXPy, the black curve. It is 6 times better than UCXPy for 1 byte message. The right-hand graph is presenting performance of large messages from 512 kilobytes to 128 megabytes. The y-axis here is bandwidth in gigabits per second. Again, MPI for Dask is achieving higher bandwidth than UCXPy. It is roughly 4 times higher for message size of 128 megabytes. UCXPy can execute in polling and event modes. Since the polling mode is efficient, we are only showing the polling mode in this comparison. The first benchmark is the sum of Coupa array with its transpose. This is a communication intensive benchmark and a great way to compare the performance of different communication devices in Dask. These numbers were taken on the in-house cluster called RI2 with NVIDIA V100 GPUs. This benchmark is presenting strong scaling results. The x-axis in these plots represents the number of Dask workers. The left-hand plot has the total execution time in seconds as the y-axis. As can be seen, the red bar that is representing MPI for Dask is better than IP over IB and UCX. It is 3.47 times better than UCX on average. IP over IB is representing the TCP device here, since we ran it over InfiniBand using IP emulation. The right-hand plot has the communication time in seconds as the y-axis. As can be seen, the red bar representing MPI for Dask is better than IP over IB and UCX. It is 6.92 times better than UCX on average. This is the same Coupa benchmark on the TAG Frontera GPU system with NVIDIA Quadro RTX 5000 GPUs. Again, the x-axis in these plots represent the number of Dask workers, but now we utilize 32 Dask workers. The plot has the total execution time in seconds as the y-axis. As can be seen, the red bar that is representing MPI for Dask is better than other communication backends. It is roughly 1.71 times better than UCX on average. The second benchmark is the QDF merge operation. These numbers were taken on our in-house cluster called RI2 with NVIDIA V100 GPUs. This benchmark is presenting weak scaling results. The x-axis in these plots represent the number of Dask workers. The left-hand plot has the total execution time in seconds as the y-axis. As can be seen, the red bar that is representing MPI for Dask is better than IP over IB and UCX. It is roughly 3.11 times better than UCX on average. The right-hand plot has the communication time in seconds as the y-axis. As can be seen, the red bar representing MPI for Dask is better than other devices. It is 3.22 times better than UCX on average. This is the same CUDF benchmark on the TAG Frontera GPU system with NVIDIA Quadro RTX 5000 GPUs. Again, the x-axis in these plots represent the number of Dask workers, but now we utilize 32 Dask workers. The left-hand plot has the total execution time in seconds as the y-axis. As can be seen, the red bar that is representing MPI for Dask is better than other backends. It is 2.91 times better than UCX on average. The right-hand plot has the merge throughput in gigabytes per second. This is essentially the inverse of the left-hand side graph. Again, we observe that MPI for Dask is 2.9 times better than UCX on average. This section of the talks presents a summary and conclude the talk. This paper presented MPI for Dask, which is an MPI-2 GDR-based communication device for Dask. MPI for Dask is built using MPI for Pi and provides efficient communication between GPUs. This is the first effort to implement MPI-based communication coroutines for Python applications. We demonstrated efficient performance of MPI for Dask against other communication devices using basic communication and application benchmarks. We recently released MPI for Dask 0.2 in March 2021. This can be downloaded from our HiBD website from this URL. Also, we have generated a pull request on the Dask distributed GitHub repo in an effort to get this work merged upstream. With this, I conclude my talk and thank you all for listening. Please feel free to contact me on my email with any comments and questions that you might have. Thank you.